Welcome to Lecture 1 Supplement, which is entitled Professionalism for Graduate Students. This is the course on ethics in engineering, and in particular, I'm Professor Kevin Passano. We'll be talking about issues connected to Lecture 1, but primarily for graduate students in this supplement. Particular, the professionalism for postgraduate case, that would be after a Bachelor of Science, in particular focusing on students during their master's or PhD programs or after those students gotten their degrees. We have for this case a focus on, however, professionalism in graduate school, that is during the MS or PhD program, but there's going to be a lot of cases throughout the class where there will be differences between the undergraduate and graduate cases, such as in cases of competence. We'd expect a higher amount of competence out of master's and PhD degree holders, and therefore, in a sense, a higher ethical behavior. There's sort of higher professional standards. And you'll begin to get a sense of that after you see what we talk about with respect to the program itself in the master's or PhD. So, what are those higher standards? Those higher standards, as I mentioned a moment ago, are competence. We expect a higher competence out of a master's or PhD student or holder. This will impact an ability to act in a more ethical way. In other words, this will be found in the issue of the impact of competence on reducing the adverse impacts in trade-offs in safety. A master's or PhD student may be able to come up with sort of a better trade-off. In other words, they may be able to enhance safety at a lower cost. For instance, in an ABS system design, an anti-skid braking system design, called mechanical design, you may find a situation where a team of master's and PhD students may be able to design a product that has much better safety standards and at a lower cost. It's more robust than, for instance, a team of bachelor's students. The second piece of professionalism, as we talked about in Lecture 1, is conduct. So remember, professionalism is competence and conduct. So with respect to conduct, you sort of expect a higher maturity from graduate students and higher degree holders. There are certainly higher expectations for a master's or PhD, that play out in many ways in the job, such as often bachelor or master's or PhD holders are put in charge of groups and expected to behave with a very high level of professional behavior. Sometimes when the PhD is held, they will call you Dr. So-and-so. And there's really a need to meet the higher standard that's implied by that term. Next, some examples, MS and PhDs on the job. Example 1, MS graduate is expected to be a Master of Science in Engineering. So what does a master mean? Well, it means that you're well-read, okay, in technical things, of course, highly technical. You sort of know the whole area. You know other approaches, etc., and you really are top-notch expert or master in your field of study or the product that your company puts out. And your coworkers perceive you that way. They look at you as an expert so that when they get stuck on things, they go to you for answers. And that's really a great form of a compliment when an engineer goes to another engineer for a question. And really, somebody with a master's should be someone like that. And the type of things that people in engineering would say about somebody that's truly a master or an expert at something is she knows everything about that subject, or she's at the cutting edge of technology in her field. Those are the kind of compliments that engineers pay each other when they're highly technical competent. So the conduct should be consistent with high competence. Okay, and again, as I mentioned a moment ago, the master's person often ends up being a manager or a boss for a technical area generally. For instance, for bachelor's or other masters. Now, let's assume a non-academic career and consider example number 2. Someone gets a PhD in engineering. This is sort of everything for the masters, plus you're expected to create new technologies, new concepts, new processes, sort of first ever things. You really, a PhD should be leading a field. This term, in fact, philosophy, at first might be a little confusing, but in the context of engineering, but really what it means is that you have a deep and a broad view of the field. You, as a PhD, would know where the technology has been in the past, where it's going in terms of general trends, and what broad impacts it might make on the market, society, and the environment, for instance. And again, your conduct should be consistent with your high competence. Again, this person is often a boss or a leader in a company and nationally or internationally. Often they lead a group of bachelor's, master's, and other PhDs as a boss. And often they would be one of the most well-respected individuals in a company for a non-academic career. Next, for an academic career, this is example 3. We have the Doctor of Philosophy, and we want to talk about what professionalism means in this case. Well, this person's going to create a research program to create new math techniques, technologies, and of course, new graduate students. They're going to do teaching in a classroom in a professional manner in front of the students, and do service to, for instance, their professional organization or their local community. Now, the levels in the U.S. Are an assistant professor for the first 7 years. That's the position that is taken by a new academic recruit. And then second of all, an associate professor. That's someone who has tenure. Tenure meaning they have their job is as permanent as their department is. And then full professor, usually obtained after 11 or 12 years, and that's the highest rank of professor. For that, you would have to become an international expert in your field of study. An associate professor is usually given that position for good teaching and service and excellent research in making significant new contributions in a particular area. Okay. Now, of course, in an academic career, conduct of a professor has to be consistent with the high competence. That type of conduct means how you treat your other colleagues, your graduate students, in particular how you treat students. Basically, it's the standards are high because it is expected that as a professional you will set a good example for your students. Now, engineering in non-engineering fields. A lot of people in engineering switch fields. So after a BS or then an MS or PhD in engineering, they go to medical school. Okay. Now, some that go to medical school go there with the intent of doing research. Others want to be a clinician and work with people. So some engineers go one of both those directions. Some go into law. Often the engineer that goes into law goes into patent law, and then some engineers get an MBA or Master's of Business Administration. That is after, let's say 5 years of engineering practice, get an MBA, move into the business side of your company. That's a common career path in engineering. And each of these has its own ethical and professional standards. So if you go back up to medical school, of course, medicine has its own standards for professional behavior, as does law school, people in law school, lawyers, and in business school. Okay, so you sort of adopt a second set of standards. These standards are all about applied ethics. Engineering ethics is a type of applied ethics, as is medical ethics, or legal ethics, or business ethics. Okay. But again, though, we have very high standards of professionalism for these fields, and high standards for in that professionalism come again in two forms: in the form of competence, being a competent engineer slash lawyer, or engineer slash business person, or engineer slash clinician, and conduct, of course, too. How you treat other people, and how you hold paramount your clients' welfare. Now, professionalism in engineering grad school, well, at Ohio State, for instance, you have to get to know your professional environment. You got to get to know the OSU campus, go through an orientation for grad students, study, if you're an electrical engineer, for instance, study the ECU website. If you're mechanical, study a different website. You make course choices. A professional engineer would not take the easy way out all the time. It would take, the tough classes, the tough professors, and get a good variety. You might talk to students and faculty that help in choosing. Next, you graduate students, you have to think about how to find an advisor. You might talk to graduate students about it, sort of get the scoop, as they say. You might want to find out some characteristics of that advisor, whether they're hands-on or hands-off, meaning how much help are they going to give you? Are they going to work closely with you, or are they going to be at a significant distance and let you do everything? Are they young or senior? Some people have different preferences in that respect. Next, how does the match? You have a certain experimental theory mix that you're interested in. Well, does it fit your advisors? Is your advisor a theorist only, and that you have in mind picking this advisor, and yet you're an experimentalist? So you got to be careful. Then you got to work on matching research objectives and directions to your own interests. Can you match personalities? You feel like you can work with this person? Funding is often a key issue, trying to get funding, and is often a basic topic for discussion early on. So how should you contact a professor? If you're taking a class with them, see them after class. Emails could work for some advisors. Some it won't work because they get so many emails from students asking them questions they can't keep up with them. So you might consider just stopping by their office. Next, early on, let's say you've chosen your advisor. You want to give your advisor confidence in you. You might offer to do a mini research project to show your skills, or she or he may give you an initial problem to work on. For the problem, research the literature, think deeply about it, find solutions on your own, and be prepared to show the logic of your work. In other words, why you discarded one solution in favor of another. Be prepared to say what the next steps are. go far beyond the expectations that were set out when this problem was handed to you. Challenge your advisor politely. In other words, ask them questions about the problem and so forth. Build trust. So if you are working on a problem but you don't have any progress this week, explain why and keep open communications. Okay? Don't let them think that you're just disappearing. The advisor, what you should be seeking to do is to create a lifelong relationship. Advisors often become good friends. They write you recommendation letters for many years, and sometimes they can really help you with your career. So this is someone you're going to get to know very, very well and work with quite a bit. Next, professional behavior in class. Prepare for each class. Read ahead, not just the textbook and handouts, and generally don't ask the professor how to prepare or what to read. You figure out what to prepare and read. Go to all the classes. You are responsible for everything being said, so don't skip class. Be on time or early, okay? In other words, class will start on time almost always, and you should be there. You should not come into class late. And generally speaking, in connection to going to classes, grad students don't skip class like undergrads do. Grad students maintain a much higher level of professionalism with respect to class and going to class and how they participate. They answer or ask questions. And keep in mind, professors know that they may say there's no dumb questions because they don't want to scare people off and be afraid to ask questions. But you know what? There are dumb questions. So don't ask them, okay? Ask good questions. Think carefully before you ask a question. And try to ask a good question so you really are learning. Okay. Next, written assignments. Do assignments early so that you have time for questions. Don't ask last-minute questions. Don't go into the professor's office 15 minutes before class when an assignment is due and ask a question about a homework. It shows you're being unprofessional. You should be done way ahead. You should be using LaTeX, not Microsoft Word, for your assignments. Next, good enough is an A in grad school, but don't aim for just doing good enough. Aim for higher than an A. Do more than is asked of you. In other words, you're asked to do something, let's say, run one more simulation than was asked. Investigate a different idea. With a bit of effort, your assignment can be quite impressive. Usually when you're done with an assignment, it's easy to add a lot of other solutions and investigations to that assignment. Won't take you much time, but is really very impressive for a professor, and it contributes greatly to your learning. Generally, the policy on working together, you've got to get it clarified and then give credit to others if you work with them. Know what the policy is up front. If the professor doesn't state it, ask them. This is very important because you don't want to run into some type of serious ethical issue here, that one that we'll discuss more later in class, where you're accused of cheating or copying off of someone else. Next, the rules. Well, the rules are in, for instance, if you're electrical engineering, a graduate student handbook, know it. It's your responsibility to plan and track your progress towards your degree. Make sure the requirements are fulfilled, not your faculty advisor's responsibility. You have to lead the show there. If some rules are not clear, ask the staff first. Next, to pick committees for the PhD qualifier, candidacy, and exam committees, you work with your advisor. You do not just go pick the committee yourself. You work with your advisor and make sure that he or she agrees with your choices, because sometimes there's sticky issues in making these choices, and you want to make sure that you're making a good choice because it'll affect the outcome of your exam. Okay, so next, the way this master's program, this is a very standard master's program I'm going to describe, is usually less than 2 years after the bachelor's. There's the non-thesis examination that is managed, um, by a variety of people, in particular Dr. Fiorentini and Dr. Viorel. Then there's a thesis. This is not as common. Usually you take classes to make you an expert, but more the research starts at a low level, and then you do a lot of research in the summer, and then for another 1.5 semesters, and you write it up, or you write a paper, and then you defend it. Usually give it a 20-minute talk and then 40 minutes of questions. And you work on this thesis very closely with your advisor, who's what you call your research supervisor. The professionalism issues that arise here are that there's got to be an independence in assessing the literature, addressing problems without having your advisor hold your hand, okay? And you have to have professional communications, okay? It has to be good professional technical writing, for instance, good professional technical oral presentation, for instance. Next, the PhD, which takes about 5 years after the bachelor's. The independence level is much higher. You work a lot. You be a scholar. There's the PhD, in the early part of it, there's the PhD qualifying examination, where you have to prepare well for that. And then there's classes. You have a variety of those. But it's not that many compared to the overall program, so you don't get a PhD on A's in classes. You get a PhD primarily based on your research. So what you have to do is you have to learn to self-learn. You have to learn how to learn yourself. You should read voraciously in technical literature. Try to read top people, those are top researchers, and top papers. But keep in mind that there's no gods in academia. They're all normal people, of course. You should be going to some seminars given by the department or your group, and you should try to create an intellectual environment with your colleagues. The next step in this program is the PhD Candidacy Examination, which has a deep literature treatment, and you have to show definite progress towards the dissertation. This might come in the form of enough results to, for instance, constitute a journal paper, even in some cases. And then there has to be a research plan. Next, the dissertation research, which is the core activity of the PhD, takes about a year post candidacy by most people. Sometimes you can multitask on the various problems you said you were going to work on in your candidacy. Whatever you do, you search for elegant ideas and solutions. And then finally, you have the final dissertation defense. This should be highly professional. You should basically walk into this meeting where you feel like you know the subject that you're talking about better than anyone else in the world. And therefore, it shouldn't be a stressful exam, because you should be able to answer anybody's question that's in the room quite easily. Next, publishable work that might come out of this. You should be a high amount of creativity in your PhD dissertation research, creating new things, and not just insignificant new things, but significant new things as measured by impact on the field and practice. So you will see early on back at the PhD Candidacy Examination that you need a proper literature assessment to argue that you have novelty. You'll fine-tune that literature assessment by the time the dissertation is written, perhaps, but it is very important for you, because it is on that basis of the assessment of literature that you're going to make your claim of novelty, which is crucial, because that's what gets you your PhD. All right, that finishes the lecture, I just wanted to point out that some of the points later in the talk came from this document, PhD Research Elements of Excellence by Professor Schroff in the Department of Electrical and Computer Engineering at Ohio State. That concludes the lecture, except for there was one more thing. There's the view check question, and that is name a famous engineer, not the ones listed at the end of lecture 1, who has a graduate degree, MS or PhD. And I'll give you a hint. At the end of lecture 1, in the slide with the collage of pictures, there's at least one of those that has a PhD. Thank you. Goodbye.